an image, and I just typed cat on left. And here it's predicting which object in the image I was referring to. Now cat on right, black and white cat. Here's another image, I don't know if you can see it very well. Woman, it's that object. Girl. So it's doing both bounding box detection and segmentation as well. Child in orange. Right. So you can see as I type in different expressions, it's identifying different objects in the image. And here it's showing the weights that it's predicting for each module, for each word as well. Okay, and then the last task I wanted to talk about a little bit is visual question answering, and this has been really popular in recent years. So for visual question answering, we built this data set called Visual Mad Libs. I don't know if any of you have played Mad Libs as a child. It's like this fill in the blank thing which you play with two people where you say, give me a place, give me an action verb, and then you sort of fill in these blanks. And so our data set is also like that. It's a fill in the blank thing where you ask a mechanical Turker to fill in a blank, or you might say this place is a blank, and then you ask the Turker to fill in the answer. And you're asking them to describe the type of scene shown in the picture. These prompts are instantiated automatically based on the objects in the picture, and the collection strategy, we have a number of different prompts, is designed to cover a range of different types of information. So here are the Mad Libs that we collected for this image. This place is a park. Person A is wearing blue shorts. Person A is blocking person B, and so on and so forth. So you can collect a number of different types of information about each of the objects, as well as relationships between objects. So our data set is pretty big. It's about 360,000 descriptions for 10,000 images with 12 different types of fill-in-the-blank descriptions. So given this data set, we can actually work on a couple of different tasks. One of them is focused description generation. So we can ask the computer to write a description about particular objects in the image or relationships between objects. The cat is black and furry, or the cat is sitting on a chair, or the person is playing chess with the cat. We can also look at the question answering task. So now we give the computer a question with a blank, and they have to choose from a set of answers for what things should fill in the blank. So the person is like the dog. Well, probably it's sharing his cupcake with, not sleeping next to. One nice aspect of this kind of problem is that it makes evaluation really easy. When you're trying to evaluate, how good is a caption for an image, so that's a much more difficult thing than just scoring a multiple choice test. Here are some examples of a simple baseline for the question answering task. The person is a competitive skier with an orange hat, or sitting on a chair. Once we built this data set for images, we thought, well, how about videos? And we wanted to explore visual question answering in videos. So this is something that we just released 2 days ago. This is the TVQA data set for localized compositional video question answering. And it's available at tvqa.cs.unc.edu, and it's going to be at EMNLP this fall. So the TVQA data set is built on video clips from 6 different TV shows over a range of genres, from comedy to crime. And it contains about 152,000 multiple choice questions spanning over 460 hours of video. The questions are sort of 2-part or compositional, so that you have to both localize where in a video clip the question is talking about, and then also answer the question. And so we provide both sort of long video clips as well as like timestamp annotations for where in the clip that is the most relevant part of the video. And I don't think there's any sound here, but this is like a full clip. From friends, it's about a minute long though. Maybe there's captions on this one. Okay. So it also comes with subtitles so that the computer can understand the dialogue that's happening. This is like a full clip. Here's a localized piece of it that's most relevant for this question. And here you can see the subtitles in the localized clip. And so the computer has to answer a question like, what does Rachel do with her hand when she asked Ross why he never said anything to her? The answer is she points her finger at him. I don't know if you can see that in the localized clip there. And so what you have to do in this task is localize where in the 60 seconds that occurred, and then both understand the dialogue as well as understand the motion of her hand in order to answer that question. We also provide some baselines, including a baseline model that sort of has two different streams based on the subtitle as well as based on the video. And it combines information from both of these streams to answer the question. Yeah, like I said, you can download it, and we'd love it if people would play around with it. Hopefully we're going to host a challenge soon on this data set. There's been a ton of interest on EQA, obviously. There's lots of other existing data sets, both on images, sometimes even multilingual, as well as videos, and even some sort of embodied question answering where you have a robot that has to drive around in the world and then answer a question based on what it finds. Cool. So that was like a very fast introduction to a lot of different tasks in vision and language. These days I'm sort of thinking about what's coming next. And one of the things that I think is really interesting is bringing vision and language into the real world. So can we interactively generate and interpret and act maybe on natural language in the real world? This comes with a number of challenges. We're moving from internet type images to the real world where recognition might be much more difficult. We have to make things real time because we can't wait 10 minutes for it to come up with an answer. It has to be answering and talking to you as it goes around. Obviously data and evaluation become much more difficult as well. Because how do you evaluate an interactive system? That's much more difficult than evaluating a static system. And if you want it to be a robot, maybe you have to now deal with manipulation. And that's a whole other task that's also difficult. We started working on this a little bit with our MatNet. So this is a Baxter robot, and a person is talking to it. It would have sound, but it's showing you what he's saying. So I think he said something about like pick up the red cup and put it in the bowl or something. Grab the white cup and put it into the green bowl. So now the robot is both interpreting what he's saying and translating it into what it should do in the real world. We speed it up a little bit because it's just slightly slow. And you imagine the Baxter robot has both RGB input and also can have things like a depth sensor, so it can tell where things are on this table. This is my student Lee Cheng, who's been doing a lot of the refrain expression work. Getting things to work on robots is both simple and difficult. One of the challenges is that the manipulators are not great, so you kind of have a limited set of objects that you can work with. Here's some more examples. So you can see it's understanding that refrain expression about the cup next to the yellow bottle. So that's what we've been working on and are really excited about.